Hi, everyone. Good to see you as you're coming in. I think we'll just give it 1 or 2 more minutes to let people keep entering the Zoom call, and then we'll get going. Great. So hi, everyone. I think the numbers are leveling off now. Great to welcome you to the first Rocky Worlds discussion meeting of 2023. It's fantastic to be back, and there's a series of talks we're continuing planning and already scheduled for the year ahead. So great that you're joining us for the first one, and do kind of keep your eyes out for the reminders and on the website for what's coming up. And just actually as a reminder, also the talks we've had so far kind of archived on YouTube, and we're live streaming again to YouTube today. So if you have to leave early today, you can catch up on YouTube, see what was said. So yeah, you can see us here and there. So it's my great pleasure to welcome Nienke van der Marel to the Rocky Worlds discussion today. Nienke is an expert in protoplanetary disk observations, relating the structures in disks to dynamical processes and chemical processes that give rise to planets forming, and has done some really exciting work in that area. So it's fantastic. He's joining us today to put all that protoplanetary disk work in the context of rocky planet formation, kind of for the community here. So I'll stop sharing, hand over to you, Nienke, and thank you again for joining us.
Thank you. Yeah, let me. So do you have the right view? Okay.
Yeah, that is perfect.
Good. Okay, so yeah, hi everyone, and thanks to the organizers for inviting me for the Rocky Worlds discussions. Indeed, this is a somewhat different community for me, coming from protoplanetary disks, but I've tried to do my best to kind of summarize some of our major findings from the last 5 years or so in that context of rocky planet formation. So if I think of planet formation, I usually think of this particular image, kind of basically the problem. How do we grow from tiny little dust grains of a micrometer in size to pebbles, rocks, planetesimals, rocky cores, and then maybe even make the next step to gas giant planets. And then finally, through migration and scattering events, how do those planets actually end up at the locations where they are today in the exoplanet distribution through migration and scattering? And one of the main problems here for me as an observer is that only the first steps, so basically the growth from tiny dust grains to pebbles, is observable through observations, for example, with ALMA. And the final product, so the exoplanet distribution, is observable. But all these steps in between are not cannot really be observed directly. We cannot see how many planetesimals there are in a protoplanetary disk, and so therefore the quantification is constrained by theory. But of course, these theoretical models need our input from, like, what are the initial conditions in the disks, like, for example, masses, timescales, radial scales, like how things are distributed, trends, but also exoplanet populations and occurrence rates. So these inputs are necessary in order to constrain the theory and come to a final model that actually explains us how planets form. And yeah, so this picture is, you could say, is quite specifically for gas giant formation. And so we kind of know from the lifetime of protoplanetary disks of several million years that the gas giant planet formation process must happen relatively quickly, like in several million years. And we see that in the blue curve. So the initial dust growth and then going up to planetesimals, that's more or less the same, whether you are forming a gas giant or a rocky planet. But then the gas giant process must happen rather quickly. And the general view is that for a rocky planet, they can, in principle, form much later because they don't need to accrete any gas. They can just grow very, very slowly when the gas in the disk has long dissipated, and this is causing this kind of separation in possible different formation paths. But we will see if this is actually the case. So to take a little step back, let's go to the basic picture of star and planet formation, and including the formation of the protoplanetary disk. So we think that this process starts with the gravitational collapse of a cloud into a so-called prestellar core that will turn slowly into a protostar surrounded by an accretion disk that is still feeding the material from the envelope onto the disk, onto the star, and at the same time a jet from the star will remove a lot of the cloud material as well. And then after around 1 million years, in most cases, you're left with just a protoplanetary disk where the cloud is entirely gone. So this disk will live for several million years until also most of the material there is gone. And then we're left with a planetary system, potentially also with a debris disk. And in this talk, we will focus primarily on this stage, the protoplanetary disk, so the disks that are between sort of 1 and 10 million years old. So protoplanetary disk from the side looks more or less like this. So we have large dust grains that we think are mostly settled to the midplane. But we also have gas and small grains that are distributed more throughout the disk and that are also more vertically extended. And so therefore we for example, CO emission lines, we are more often tracing the surface layers of the disk, and the same for infrared scattered light images where we're tracing the small dust grains. While in ALMA submillimeter continuum, we are really tracing these large dust grains that are mostly settled. So this is just a way of thinking, like, what are we tracing at different wavelengths? And so this is also illustrated in these observations. So here we see on the left a scattered light image. This is all the same protoplanetary disk on the same spatial scale. So the scattered light image shows several rings of the small grain dust distribution, while the ALMA millimeter continuum shows a much more compact millimeter dust disk, while the integrated 12CO emission that is tracing the gas is again much more extended. So essentially these different observations also show different components, and clearly these different components of gas, small and large dust also are differently distributed throughout the disk. Now, to go a little bit more into the processes here, let me first introduce you to a beautiful gallery of some of the most famous ALMA disk observations. So these are all continuum observations of the millimeter dust distribution, and all taken at high angular resolution, where we see all these beautiful substructures in the millimeter dust. So we see rings, gaps, large inner cavities, asymmetries in some of these cases. So there's a very large diversity of substructures. And now the question is, of course, what is causing these substructures? And in order to explain that, I need to take you back to basically the 70s, when Leiden realized that there was a problem with dust evolution in a protoplanetary disk. Because if we think of a smooth protoplanetary disk, there are no gaps or whatsoever. We would, due to the gas surface density and temperature dropping radially outwards, we essentially have a negative pressure gradient. And because of that gradient, the gas and also the small grains coupled to that gas are not moving capillarian. They're moving a little bit slower. We call this subcapillarian motion, and we see that here in the figure. However, larger grains that have grown, for example, through coagulation, they are decoupled from the gas. So therefore, they don't feel this pressure gradient. They want to move capillarian, but they're surrounded by all this somewhat slowly moving material. So while they're rotating, they're constantly experiencing a headwind. And therefore, they lose angular momentum and move inwards towards essentially the higher pressure. And this problem, which is that as soon as you have large grains, they will move inward, is also called the radial drift problem. And essentially, this is limiting the potential of growing planets, because as soon as you grow to basically a millimeter size in the outer part of the protoplanetary disk, the millimeter sized particle will drift inwards on really short timescales. So you need something like a pressure bump, a pressure maximum in the outer disk to prevent this drift from happening. Well, and it's been proposed that this pressure bump can arise if you have a gap in the protoplanetary disk in the gas distribution. For example, if a planet is formed, it will carve a gap, and then at the outer edge of that gap, you naturally get a pressure bump where the dust particles will concentrate. Because remember, the large particles always move towards high pressure, but then because of the positive pressure gradient on the opposite side, on the inner side, they will remain there. In this way, you would get a dust ring. And then on the right, I also have a little hydrodynamic simulation of a radial pressure bump that becomes a Rossby wave unstable. And this can lead to the formation of large-scale vortices, which are these azimuthal structures you see now arising alongside the planet orbit. And these are essentially azimuthal overdensities in the gas that trap the dust in both the radial and azimuthal direction. So now you have an azimuthal dust trap. And the reason that, or the way that we realize that all these rings and asymmetries in ALMA observations are dust traps is because we were able to compare the millimeter dust distribution, which we see in the left panel here of both disks. We see that the millimeter grains are much more concentrated than the gas and the small dust grains that are traced with 13CO and infrared emission. And here we see essentially two cases, one of radial trapping, a narrow dust ring, and one of azimuthal trapping, an azimuthal concentration compared to the distribution of the gas and the small grains. So it's really the segregation between the different components that tells us that these are dust traps, and that therefore all these structures can be interpreted as dust traps. Well, why do we think that these gaps are caused by planets? Well, there are now two systems, PDS-70 and ABO Righe, where a protoplanet has been directly imaged by high contrast imaging. And then there are a number of indirect signatures, for example, spiral arms and scattered light images, gas gaps in 13CO emission, and also kinks and blobs in the kinematics of several of these disks that all are located inside the dust gap. Well, I have to add here that these gaps are typically tens of AU in size, and therefore, any planets must also be located at these really wide orbits. And considering how big these signatures are, or the protoplanets itself, these must be fairly massive planets, really Jovian or even super Jovian planets. So I realize we are diverging a bit from rocky planet formation, but I'll come back to it. I have a point here. Because what is the minimum mass that you need in order to create a dust trap? Well, this is has been figured out by various people in simulations. Essentially, the minimum planet mass to create a dust trap at tens of AU, large radii, is about 10 to 20 Earth masses. So you don't need a Jupiter planet in order to create a gap. This is to create that dust trap. This is just the planet may eventually grow to such a very large size. And the fact that we are observing these gaps in disks that are only 1 million years old means that core formation of sort of 10 to 20 Earth mass cores must happen very rapidly in less than 1 million years. Well, the interesting thing, of course, about this mass limit, this pebble isolation mass, is that the fact that it's massive enough to halt the pebbles from drifting inwards to create a dust trap, that is essentially also the moment that the gas accretion can start, because pebbles are no longer accreting onto the planet. Therefore, the surface is no longer heated. And this means that gas can efficiently accrete and the whole thing can contract and therefore form eventually a gas giant planet. So this, the way to see this process is really that you initially form a rocky core up to this pebble isolation mass. You halt the dust pebbles there, you create a dust ring, and then you start to accrete the gas and create a much larger and deeper gap also in the gas distribution of the disk. So all of this means that if we now go back to this picture where we said, oh, well, gas giants must form very quickly, but rocky planets can form much later. That is still true. And gas giant planets, may, or at least the cores of the gas giant planets, may have to form even more rapidly because of the gaps and rings that we're seeing in the disks. But the rocky planets, maybe they even form quickly as well, but they will not leave a signature in the protoplanetary disk that we will observe as rings and gaps. So they don't have to. We don't have to assume that the rocky planets form late at 10 or even 100 million years. Maybe they happen quickly. That happens quickly as well. So where can we form these rocky cores? So if we say that we already have some planets forming, and now we have these concentrations of dust in the dust traps, maybe the material that is located in the dust trap can actually grow to a next generation of planets. And so the way that this would work is essentially that through the streaming instability, so in a concentration of dust, streaming instability kicks in, you can form planetesimals. And there's even some observational evidence for that in one of these disks with dust rings where the optical depth is such, it's around 0.4, 0.3, 0.4 in value, that is actually consistent with a model where millimeter dust has already grown into planetesimals. And then basically from planetesimals, you may be able to continue growing to rocky cores. And at this point, there's still a lot of debate in the community how that would actually happen, because there's planetesimals accreting by itself. So in that way, growing to larger sizes, but that process is rather slow. The alternative process of pebble accretion, where you, as soon as you have one core and then accrete pebbles on top of it, may be more efficient, but still the timescales are still relatively long at the large radii where we see these dust traps. But there are some very recent results, and actually one result only came out yesterday on arXiv, that polydispersed pebble accretion, so distribution of different pebble sizes, and also vertical settling may speed up the pebble accretion process. So this may be a feasible way to form rocky cores, rocky planets inside these dust straps. Okay, well, all of this is interesting in case a planet has already formed and created these dust straps in the disk. But what happens if such a planet doesn't form? Well, it is you can simulate with dust evolution. This was a model run by Paula Pinilla, showing how the grain sizes change as function of time, as a function of distance from the host star, when the disk simply evolves over time. So what we see now is that the dust particles will collide with each other, and then through a balance of fragmentation and coagulation, they will grow to larger sizes. But also, because there are no dust traps, most of the dust will actually drift inwards. So you see that most of the larger dust grains end up in the very inner part of the protoplanetary disk. So now we have a so-called drift-dominated disk without rings. And the reason that we know that radial drift is happening, at least to some extent in disk, is simply by looking at this basic image again. It's just, you see that the millimeter dust continuum is much smaller than the distribution of the 12CO. So the millimeter dust particles have drifted inwards. In this case, there are still dust rings visible. So they drift inwards and then eventually they're halted. The drift itself is already evident right here from gas versus dust observations. And there are now many examples of that. But yeah, so this raises a bit the question, like we have now kind of two options. Either a disk is drift dominated, and in that case, it becomes very compact over time. We see that here on the left. Or alternatively, if we have a dust trap in the disk, for example, because a giant planet has already formed, in that case, your dust ring kind of remains. And what's even more interesting here is if we look at the dust mass, the total dust mass in the disk in these two different scenarios. So in the left case, a drift-dominated disk, the total dust mass will initially just build up because you're growing your grains up to about 1 million years. But then your dust mass quickly goes down, essentially because of the radial drift, of losing dust into the star. But if you have a dust trap, you maintain your dust mass. So these are just predictions from dust evolution models. Now, to test this, we can now take a look at the results from large disk surveys, also with ALMA. So these are snapshot surveys of about 1 to 2 minutes integration per source, making low resolution images of hundreds of disks in nearby star forming regions. And the continuum flux provides us with a dust mass and also some information about the morphology of each of these disks. So we can now do a bit of statistics of this dust mass as a function of evolution over 1 to 10 million years. So what we see in the cumulative dust mass diagram for essentially the clusters of different ages is that the dust masses in the young regions, so here shown in red, are much higher than the dust masses in older regions. So the disk dust mass decreases with age. And the dust mass itself is calculated from this rather simple flux conversion. Then another thing that we can look at is the disk dust mass correlation with the stellar mass. So we see in all these different clusters that there is some scatter, but there is a correlation. So higher mass stars have higher mass disks, and this correlation actually steepens over time. So what this means is that the decrease of the dust mass with age is the strongest for the lowest mass stars. This is another important part of the puzzle. And then finally, if we look at the typical sizes of protoplanetary disks, we see that overall disk dust sizes are larger in the young regions than in the old regions. So it means that the disk dust size decreases over time as well, which would again be consistent with radial drift. Well, and so this is a little bit weird because we've seen all these beautiful images of dust traps and rings, but now if we look at the larger disk demographics, we actually see that most of these disks seem to be consistent with radial drift. So in a paper from I guess 2 years ago now, by myself and Gijs Mulders, we proposed that there are actually two types of disks. So we gathered all these data sets from all these different surveys and in one very large demographic survey. And there we show that the disks that have gaps, so those are the ones shown in colors, they maintain their dust mass. You see they're on the high end of the dust mass distribution, both in the young regions and in the old regions, more or less the same mass. But the bulk of the disk decreases in dust mass over time. And this is dominating what we're seeing in these large surveys. The bulk of the disks is drift dominated, and only, well, we calculated about 16% of the disks have large scale gaps that are able to resist the radial drift and that have dust traps. And well, in this work, we actually did some comparison with exoplanet demographics, looking at like what is the occurrence rate of giant planets. And we know from radial velocity surveys that the typical giant planets, most of giant planets are located at a few AU. But actually those giant planets are pretty rare as well. It's not 100% or even 50%, it's more on the order of like 10%. But what is so interesting now in the comparison is that both the giant exoplanet distribution and the disk demographic, disk survey population has a stellar mass dependence. So if we look at the fraction of disks as again, separated by stellar mass, so in different stellar mass bins, we see that for high mass stars, gap disks are much more common. And also for giant exoplanets, we know that they're much more commonly found around high mass stars. So it means that we can actually link them together. We only have to assume that giant planets eventually migrate inwards. And that means that, okay, we have all these gap disks that show signatures that gas giant planets are present, but that's only a small fraction of the total disk population. And maybe all these other disks, these disks that don't have dust traps, should be linked to rocky planets. And we did some attempt there as well, basically to link that compact disk population, so the black part here in this in the top plot, to the close-in super Earths, because this population, this occurrence rate, is indeed decreasing with stellar mass. These type of planets are very common around M dwarfs, and this is similar to non-gap disks. Well, the question is, of course, like, do these compact disks really exist? Are they really drift dominated? And the answer to that is that we don't know for sure, because they haven't been studied yet at very high angular resolution. There are a handful of examples in the literature. These are all disks that are only 5 to maybe 10 AU in radius. But I have an accepted ALMA program in this cycle targeting a very large number of disks where we have upper limits on their disk dust size. We know that they are less than sort of 20 AU, but they are potentially as small as 5 AU. So these compact disks may actually be the birth cradles of at least of super Earths, of rocky planets, because they which form a later stage. Of course, there's still the possibility as well that these gap disks form rocky planets or maybe even super Earths. in the very inner part. Because if we look at these ring disks and these gap disks, we often see that there is still some emission or even a lot of emission. I've encircled it here with green in the very inner parts. And this dust will probably drift inwards over time, just like the compact disks will. And what's even more relevant here is that we're really talking about the inner sort of 10 AU or so. The water snow line is in there somewhere, and we all know that a lot of things are happening for planet formation at the water snow line. So this is why that inner concentration, even in a large gap, this could be very interesting for rocky planet formation. So that's this is basically what I have about the substructures. I do want to talk a little bit more about the dust mass budget in disks, so how much material is actually present, because there have been a couple of papers on this topic, where they essentially compare the mass in dust in protoplanetary disks or in planetary cores with that in exoplanets. So and what this plot shows is the distribution of the dust mass in disks in red. It actually shows that that dust mass is lower than the amount of dust mass in exoplanets, which is strange, right? That suggests that planets must already have completely formed at this stage at 1 million years. Because they don't have much dust left anymore. And then sort of in a follow-up study, they did another comparison looking at the earlier stages, so not the class 2, but the class 0 and class 1 disks. These are the embedded disks that are still surrounded by the cloud. The dust masses there correspond much better with the exoplanet masses. So also here there is this suggestion that, okay, maybe most planets form really early, because that's the only time that there is enough material available. Well, there is a bit of a revision on that story that was published by Gijs Mulders, who said, yeah, if you do this kind of comparison, you have to be very careful, because there are selection and detection biases in both the exoplanet catalog and in the disk catalog. So first of all, in the exoplanet mass distribution, you need to correct for the fact that there is selection bias in the kind of exoplanets that are, or the kind of stars that are studied in exoplanets. And then second, detection bias to essentially also take into account all the non-detection. So really looking at occurrence rate. And if you do that, your mass distribution of exoplanets suddenly becomes a lot lower. And opposite for the protoplanetary disks here on the left, you need to do an opposite selection bias, looking only at the stars that are more than 0.5 solar masses, because these are the stars that are typically targeted by exoplanet surveys. So if you do that, if you do the corrections in both populations, you actually find, you see here in the plot on the right, that the solid mass in protoplanetary disks is actually comparable with that of exoplanets. This is still a little bit of an issue, because it implies that all the dust must be converted into planets, but at least the problem is not as bad as previously stated. Now, then you can also argue, like, how realistic is this dust mass calculation? Because it's really a very simple equation where we multiply the flux with the distance squared and then divide it by a Planck, part of the Planck function, and a dust opacity. Obviously, the dust opacity depends a lot on your assumptions on the grain size distribution and your grain size properties. So yeah, you have some wiggle room there of a factor of a few. A second part is that you, by using this equation, you're actually assuming that all your dust emission is optically thin. And if the emission is optically thick, that means that is in reality optically thick. That means that you are underestimating your dust mass. Well, this has been checked by work by Lucas Tikonich, who looked at VLA, so centimeter observations of protoplanetary disks compared with ALMA. At centimeter wavelengths, you're definitely optically thin. And what he finds is that also there is a decrease in dust mass from class 0, 1 to 2. And therefore, if this dust mass is, if we observe that the dust mass is changing, this is not just an opacity change. And there's clearly some optically thick emission. But again, the problem is not that severe. So there's still some debate on like how much dust mass is really there, but probably the issues do not seem to be as bad as previously thought. So my summary: ALMA has revealed that the giant planets likely form early, or at least the cores of the giant planet, but it remains unclear for rocky planets that are below the Pebble isolation mass, because they will simply not show any signatures in disks. ALMA has definitely shown the evidence for the dust evolution processes predicted in simulations, and dust evolution likely plays a major role in disk evolution and the potential for rocky planet formation. And then I've listed a couple of open questions that we can talk about now for the remainder of the session. How fast can rocky cores grow in drift-dominated disks? So if all the millimeter dust particles drift inwards, how quickly can we grow rocky cores in that very inner part? How fast can we grow them in dust traps once those first planets are formed? What are the true dust masses in various disk stages? I guess that's more of a question for the disk community. And also this question, do rocky planets actually form late after the gas dispersal of the disk? Or do they maybe already form in these early stages and just remain below the Pebble isolation mass, this core accretion threshold, and therefore don't continue to grow into gas giants? So with that, I'll open the floor.
Fantastic. Thank you so much for the talk and brilliant introduction to an overview of protoplanetary disks, the diversity and links to rocky planet formation. That's brilliant. So in terms of questions, we've got some fantastic kind of starting points here to think about. I'm sure other people have got questions. You can indicate you want to ask a question by putting your hand up, and then we can invite you to come forward and turn your video and audio on and ask your question, or you're welcome to write it into the chat also, in which case I can pitch the question as well. So either way is great. I'd really like to ask a question to begin with about this idea of rocky cores growing in the dust traps, presumably the traps created by larger planets is what we're imagining there. Are there any dynamical implications of growing a rocky planet sort of adjacent or in the vicinity of a giant planet in that way, using the kind of dust trap created by the giant planet? Is that sort of viable? Is it going to lead to some dynamical excitement if that?
I don't think so. So you have to remember that there's still a lot of gas present in the disk, and that would dominate the mass of the system and therefore the dynamics. So a planet would pretty much grow by itself, and the only way that it's affected is just the fact that dust pebbles feel the drag forces of the gas and the pressure gradients, but not dynamics from each other as long as the disk is still there.
And if that was an important way of generating rocky planets, does it then lead to any predictions in terms of kind of architectures of exoplanetary systems or relationships between giant planets and rocky planets in terms of orbital?
Yeah, that's the problem. Of course, initially that would mean that the rocky planets would always be located outside of a gas giant. But as soon as the disk is gone, dynamics, scattering events can flip them around. So I don't think that would be possible to constrain from much older exoplanet systems.
Yeah.
Unless we can somehow figure out the formation location from those planets originally, like where they were originally formed, maybe from the composition. That would be a possibility.
Yeah. Cool. Amy, you've got your hand up. The question.
Yeah, I was going to say just another comment on that as well. Is it probably depends on timescales, right? The core doesn't grow big enough that it then accretes gas before the gas disk is gone, and you get two giant planets, right?
Yeah, but it needs to be above a certain mass before that even happens, right?
So I just wanted to ask you about the we're trying to work out when things start growing, right, from the dust masses. Did you have any thoughts on how maybe we can distinguish between growth, as in from dust to bigger dust that we can't see, or even planetesimals, versus growth from that to planets, right? There's just no way, is there, really?
No, not really. No.
So actually, you could just be tracing planetesimal formation in those early
it's
phases.
possible, like in this, and there is some, there is this the paper that I mentioned from Stamler. Go back to that. So he says that at least for this disk, we have some measurement of the optical depth in the ring, like the continuum optical depth. And he says that according to dust evolution, if you don't have planetesimal formation, that means that grains stay relatively small. Your dust opacity would, your dust optical depth would have to be much higher than what is observed. And only if you include planetesimal formation, you would get such a low optical depth. Of course, this depends on your dust evolution model, and I'm assuming that there's still so many knobs to turn that you could in principle get around it, but to observe it directly, I don't think so. I don't think there's a clear way of doing that.
Thanks.
Caroline.
Hi, yeah, thank you for the talk. I was wondering, when you don't yet have a planet in a disk, what are the alternative ways to form a dust trap?
So there have been many mechanisms proposed for generating pressure bumps in disks. Most of these have to do with magnetohydrodynamic effects and instabilities in MHD simulations. It seems like there are many ways to generate pressure bumps, so therefore you could say that everything that we're observing has nothing to do with planets. On the other hand, the fact that we see all these indirect signatures of planets, and also that the statistics seem to match reasonably well with giant exoplanets at smaller radii, I'm quite confident that at least these large-scale structures are caused by planets. But maybe, certainly in the earlier stages, when the disks are still embedded in the cloud and we actually don't have that much information about them, maybe these initial instabilities cause the first formation, like the first concentration of dust that turn into those first planets. These are for me, because I'm really an observer, I'm not a theorist. For me, these seem like a little bit of magic almost. It seems like whatever they do, they can come up with new hydrodynamic instabilities that will happen and that will generate pressure bumps. But observing them directly is actually really hard. But yes, there is a way to do that.
Thanks.
Cool. Tina, you got your hand up.
Yeah, hello. Thank you very much for your interesting talk. Just perhaps to get this right, so for my understanding, so there is the possibility that already below the dust you formed rocky planets, or let's say what we call asteroids or some things, but you just don't see them because the dust is kind of hiding it in the disk, or?
No, that's not actually the reason. The reason is simply that the way that dust emits radiation, it becomes less efficient if you go to larger sizes, because essentially if you have a whole cloud of particles, they have a lot of emitting surface, but if you all clump them together into one big rock, that has less surface. So this is the way that larger particles just become harder and in the end just impossible to observe. They don't contribute much to the emission. So this is the key problem there.
I'm also surprised. Sorry.
It's not so much that it's hiding things below. It's just that the emission from larger rocks becomes completely invisible.
Yeah, makes sense. And I'm also surprised that all what is considered is spherical, you know, that when you consider like collisions, I would guess that they're like elliptical or they're like moving through the disk.
Yeah, there are more experiments both from the computer side and also from the lab side that are looking into more like fractal dust grains, for example. And these are to some extent also implemented in these dust evolution models. For example, the sticking efficiency is very high in these models, and that is actually not what you expect if you just have two spheres colliding with each other. So it's somewhat implemented, but also a lot of it is still unknown, or basically the efficiency is not constrained.
Yeah. Thank you.
Can I ask a question as you're with us and an expert, and I suppose it's potentially quite a diverse community, the kind of nomenclature of class 0, class 1, class 2, would you mind sort of disambiguating that for us, and to what extent can we time planet formation within that chronology of?
Yeah, I realized that when I came to those plots, I should have mentioned that terminology right here. So if we look at the picture of the star and disk formation, essentially the protoplanetary disk is class 2, embedded protostar is class 1, and very deeply embedded is kind of in between the two top images. That is class 0. So yeah, I apologize for that. I should have referred back to this figure.
Not at all. Yeah. How far back in that sequence can we definitively say we've seen planet formation?
Yeah, so we now have images of class 1 disks. Like the gas is much harder to image because you get molecular lines that are self-absorbed all the time. In the dust, we have pretty good images of class 1. Actually, HL tau, this very beautiful ring disk, is a class 1 disk. So there we're fine. In the class 0 stage, it is still, things are still much more embedded and therefore much harder to observe directly. And also it seems that in the class 0 stage, the disks are actually much more vertically extended, and also materials still falling onto the disk. So then it also becomes a matter of, do you call this a disk or a rotating flattened envelope? That distinction becomes almost impossible to say. So I hope maybe that answers your question. It's from class 1 we are okay in
and I mean the inference is that there are giant planets in some class 1 disks. Is that
yeah, the fact that we see gaps in class 1 disks means that there are giant planets, or let's say giant planet cores are already present because they are halting the dust.
Does that imply that they might have started growing at the class 0 stage?
Yeah, which means in the first sort of 50,000 years.
Cool. And so just to finish my question, because I'm being very greedy, but so what? I mean, I think when I think of protoplanetary disks and think of like the dynamics and the chemistry and the relationship between two of those, I'm always thinking of something which is nice and sort of planar. So like the kind of bottom left image you're showing there, it's sort of, but if a kind of key epoch of planet formation is in that kind of pre-stellar core stage, when it's more like it seems like a more of a 3D geometry, what are the potential implications there for like where snow lines are and how chemistry is mapping through to the cores and planets and stuff?
Yeah, that becomes a lot harder to determine. I mean, I don't think we can say that planets form when it's still spherical. You do need to have that flattening somehow to get some concentration of material. And where this so you can, in that sense, you can still say, well, snow lines are located depending on the distance, like the radial distance within that flattened envelope, within that flattened disk. But of course, the star itself is much more luminous, and also the accretion bursts are creating a lot of luminosity. So that will mess up the snowline location as well. So yeah, this is definitely something that we need to investigate. Like, what are the conditions really in that embedded stage? but both from the theoretical side and the disk chemical models, but also from the observational sides, there's still very little known. And the second part, that will remain to be difficult. That is not just a matter of pointing at the right sources. This will, you're always hiding a lot of material by the envelope. So you just have to find the right tracers that will skip the envelope and you're only tracing the disk.
Cool. Yeah, really exciting. Scarlett, put your hand up.
Hiya, thank you for the talk. I was wondering whether ALMA has discovered planets. It looked like maybe it had done from the label you put on your diagram. And then if so, I was wondering, do they get added to the NASA Exoplanet Archive or not yet because they're not necessarily fully formed, or?
That's a good one. So ALMA cannot observe a planet directly. It can find signatures of planets, and then some signatures are more robust than others. So if we go back to that, I have this slide where I show, these are just a couple of examples. There are a few dozen now, I think, with indirect evidence. So like these kinks and also gaps in the gas distribution. So it seems most likely that those signatures are caused by a planet, but they're not planet detections itself.
Okay.
I suppose one other example, which I hadn't put on here, is the circumplanetary disk that was discovered with ALMA at the location of PDS 70c. So in that case, the planet was already discovered, and then circumplanetary disk at the location. So that's not really a discovery. I don't think these indirect signatures should be added to the NASA exoplanet catalog at this point, because there are still other ways to explain them. They're still often debated, also from just imaging artifacts, for example. So
do you know whether follow-up observations have been made by like radial velocity or transits based on ALMA data, or you're not sure?
Yeah, well, so radial velocity and transit would be really hard, simply because these planets are rated at 10 to the EU, right? Yeah. So and even if they were located closer, young stars are intrinsically much more variable and active. So I've been told that messes with a lot of the techniques that we can use around this. Yeah. But high contrast imaging has definitely been tried in a lot more systems. So far only succeeded in PDS 70 and ABO Righe, and lots of potential detections in other systems. But and also James Webb is going to do several more potential planets in disks, and hopefully we'll see that in the coming year.
Awesome. Yeah. Thank you very much.
Cool. I just remind, if anyone isn't able to kind of jump onto camera or audio, they're welcome to put their question into the chat. I just had one final question, sort of coming back to what, as a community, we might be kind of really focused on. That's sort of like the rocky planet formation zone of these disks. How, just like an observational question, like to what extent can ALMA actually just technically has the resolution to reach into those inner few AU and resolve what's going on there? Yeah.
so the best resolution we can do with ALMA is a few AU, which means that for most disks located at 100-200 parsec, that is the essential angular resolution limit. And yeah, second, as I mentioned, rocky planet, like Earth-like rocky planets, would not be massive enough to create a dust gap even in the ALMA disk, so we wouldn't be able to see it. The hope is that with JWST and also in the future with ELT and maybe other 30-meter class telescopes, we will be able to do these things, but not probably not with ALMA.
Cool. So it almost gets to that place, just not quite. Cool. Well, if there are no more questions, it's been great to have so much time for discussion. So thank you, Nienke, for fitting that in alongside a talk that covered so much ground. It's really, really fantastic. Just a reminder to everyone that the next talk is going to be February 2nd this year. So we're going to hear from Yasuhito Sakin, hearing about Enceladus and chemical evolution towards life on Earth. So that's what's up next, and sounds exciting. And obviously a huge thank you again to Nienke for joining us today and taking us through protoplanetary disks and the connection to rocky planets. Thanks everyone for joining. Thanks, Nienke.